Welcome back. This is a continuation of our previous video where we discussed the unit step function. In today's video, we want to introduce the ramp function and show that the ramp function is the integration of the unit step function. And also try to, well, not try to, but express the realistic unit step function with an expression. So let's go over the basic of the step function. So we see that we have a voltage on our y-axis, and we know that that is some value v naught. We know for t less than 0 and for t greater than 0, we're going to have certain values. So we can say v of t, and this is a piecewise. We know that 0 for t less than 0 and v0 for t greater than 0. Also, we can say, still a piecewise, we can say that v of t is equal to 1 for t equal to infinity and equal to 0 for t equal to negative infinity. Also, there's another property. Well, you can call the property. So u of t, let's just put that in teal. So u of t, which is equal to our unit step function right here, plus, we can put this in red, u of negative t, and we can put that in red, and that is equal to 1. So if we add both of these, 0 plus 1 is 1, and 0 plus 1 is 1, so we get 1 from negative infinity to infinity. So for the ramp function, which we have here, we can see that the ramping starts from an instance of time, which is at 0. So we can then go ahead and show that the ramp function is the integration of the unit step function. So r of t, which is our ramp, is the integration of our unit step function from negative infinity to some value of t, u of t dt. Notice that from negative infinity to 0, our ramp function is 0, and also from negative infinity to 0, our unit step function is 0. So we can then say, or we can change the limits of integration to 0, from 0 to t, u of t dt. That will give us t times u of t, and we can take that from 0 to t. So this then simplifies to the following, which is our expression for our ramp function with the ramping starting from a time instance of 0. Well, what if we want the ramping to start at some other value other from 0? Well, if that's the case, we can then go ahead and use this expression and say that our ramping function, and we can call some time instance other from t, capital T, so our ramping function we have there is equal to, so we're using the same expression that we derived, is equal to t minus t times u of t minus t. So this is for our ramping function whenever our this is for our ramp function. So this is for our time shifted ramp function if we should use the correct description. So knowing our time shifted ramp function expression, we can then express our time shifted ramp functions. So the first one we see is in teal. So we can say that r of t minus, and as you can see, our ramp function is advanced in time, which is a positive 1. So if you minus negative 1, we get a positive 1. So you could call it, you could say it like that. So that's a positive 1, and that's equal to t plus 1 times u of t plus 1. In black, we have, this time it's a delayed time-shifted ramp function. So that has to be negative 2. That's t minus 2 u of t minus 2. So here we have our time-shifted ramp function, which is advanced in time, 2 seconds. And we had the delayed time-shifted ramp function, which is, whoa, this is the delayed. So in black, we have the delayed time-shifted ramp function. And in teal, we have the advanced time-shifted ramp function. So we can then go ahead and look at a different scenario. We can start with teal again. As you can see this time, our slope here was a 1 by 1, so that's a slope of 1. And both slope were the same. As you can see, our slope was 1. So here we have a different scenario with a slope, with a different slope. So the time axis is increment of 1, and as you can see, this is an increment of 3. So in teal, we have that, and these are time shifted. So we can go ahead and use the time shifted expression. In this case, let's just write the value for the shifted. So this is delayed, so it's delayed 1, which is equal to, and now we have a slope, so rise over run. So we rise 3 and we run 1, so that's 3 volts per second. So that's going to give us 3 volts R of t. You don't have to write the R of t, but I like to write it. Well, if this case is a time shifted unit step function, so let's just write it like this. So that would be negative 1, and we would multiply that by u of t, and also this is shifted negative 1 as well. And then we go ahead and R of t, and this time we'll have a, so let's see, this is delayed, this time we'll have advance. So the black ramp function advance from 0 to 1, so that's a plus 1. So same magnitude for the slope, different sign. So that's t plus 1, u of t plus 1. So there we go. So for our negative slope, we have the expression for the advanced time-shifted ramp function. Here we have the delayed time-shifted ramp function with a slope of 3 volts per second. Now that we went over the ramp functions, so also let's just write those. So this is using the time-shifted ramp functions. However, what if we wanted to use the ramp function? Well, we could just basically write that as R of t minus 1 is equal to 3. And now we use the ramp. So as you can see, we can indicate that as this is the ramp function, time-shifted ramp function. So let's put that as t minus 1, and R of t plus 1 is equal to negative 3, R of t plus 1. So both of those describe, so both set describe each of our ramp functions. So we can then go ahead and now talk about our realistic unit step function. So if we look at the, let's just remove that. If we look at our ideal unit step function, we see that the change from 0 to v0 happens in 0 seconds. Well, in real life, that change has to take some time. So imagine we zoom out the discontinuity of our unit step function, and when we zoom it out, we see a ramp in action instead of a discontinuity. So to describe that, we wanted to know, we did want to know about the ramp function, which will help describe that. So now here we have a zoom out discontinuity, which we see the ramping. And that just indicates that it takes some time to go from 0 to some value. So we can describe that. And if we look here, we see that this goes up. So this is 2 seconds. So this is in 1 second, we have 3 volts. So this is 3 volts per second, the slope. So this has a slope of 3 volts per second. So that's 3 volts per second. We can describe that using our time shifted. Well, let's just use our ramping, not our time shifted unit step function. So if we describe that in TL, we'll get V of t is equal to 3 times r of t plus 2. So as you can see, this is the ramping function. So that ramping function is advanced in time. So that's a plus 2. And it has a slope of 3 volts per second. So now we can use another ramping function, and we want that ramping function to start from -2. Why? The ramping function continues. If we want to have a constant, we want to cancel this portion of the ramping function. So in order to do that, we'd use an other ramping function with a negative slope, and we'd start the ramping at the value at which we want to cancel the rest of this ramp function. So that would give us plus negative, so that's negative with a 3. So -3 slope, t, and that would be -2, because that's a ramp function that is delayed. And that's the expression that describes our realistic unit step function. Well, let's look at what we just did with canceling. So let's copy this so we can see it easily. Put it under here. Okay, so if we then just write some expression for these. So in black, we have a unit step function. So in black, we have a unit step function. So let's see, u of t, and that is shifted. So we're going to say that this here is -2, and this here is 2, because we're still dealing with our realistic unit step function, right? So then this would be t, and if it's advanced, this would be t plus 2. Here we have our ramping function in red with a positive slope, and remember our slope was 3. So that would be t, and that's advanced, so that's t plus 2. Here we have a delayed unit step function in blue. So it's u of t minus 2. And as you remember, we used to cancel out this portion, we would want the ramping to start from the point of which we want to cancel, which we want to cancel the rest of the ramp from this point. So we start the ramping with a negative slope from that point. So therefore we have a negative slope. So that'd be a -3. -3. And that would be t minus 2. Okay, that's that. So now we can then go ahead and show you the cancellation. So if we add this guy plus this guy, so the ramping starts from 2, right? So if we want to cancel the ramping of this guy from 2, we then use a negative slope that would cancel. So -3 plus 3 is 0, right? So we cancel that portion with this guy. So after we cancel that, you can see that there's nothing here. Remember, the unit step function is 1. So it's a step with a unit of 1. So throw away the discontinuity, and if we multiply the slope, so here we have the first two, let's just write those out so it can make more sense. So v of t is equal to, so our positive slope, the first one, so as you can see, time shifted. So working with the time shifted, right? And the time shifted expression that we had was this guy, right? So if we write out the first of the two, so in all we have 4 waveforms. The first one is the unit step function, which is in black, and then the first red ramp function. So let's write that out, u of t plus 2. So that's the first, right? So we can call that waveform 1 if we wanted to, but let's not do that. So this has a unit of 1. So if we multiply 3 times 1, we can see that we're still going to have 3. So this waveform for the unit step function automatically goes away because we multiply that, and the magnitude or the slope remains the same, right? So then if we add the unit step function in blue, that is multiplied by the ramp function in red with a negative slope, we then get this. So that's a negative slope, so that's 3t, and this is a delayed one. And then our unit step function in this case is t minus 2. So then, same thing. When we multiply 1 times 3, we'll still get a 3. And this is a negative 3, so still get negative 3. So what left is the unit step function is in black, which is added to the 0 of the ramp function, which is still 0, right? So this is this portion. And then we know that the ramping action of this guy starts from negative 2 and goes all the way up, right? Now, the ramping function with a negative slope that starts from positive 2 cancels out the rest, which remains at 0. And if it cancels at 12, we're going to get a 0 at 12. So technically, this guy here, a unit of 1, right, doesn't really contribute, right? Or you could say it's contributed, because if we go ahead and we know we multiply that, the 3 by 1, the composite function will then equal this. And the better way to show that, this is just using, a composite of, a lot of functions or graphs. The better way to show that is just using 2 ramp functions. And by using 2 ramp function is literally a little bit easier, because then we can then go ahead and just say, for instance, that the first one in red is a ramp function, and that's a delayed ramp function, so it's a plus 2. And then we go ahead in blue, this is advanced ramp function, is a negative 3 slope. It's going to be negative 2. And then we go ahead in teal. If we add those together, now you can see, so all these function is equal 0 to negative 2. So that's just remain 0, right? So 0, right, plus a slope of 3 is still going to equal 3. 0 plus a slope of 3 is still going to equal 3. So nothing changes for that slope, right? So in teal, this is a composite function, which is a composition of both of these. So then if we go ahead in teal and say that v of t is equal to 3r t plus 2 plus the negative, so that's a negative 3, and we could just write that in blue to just make it, it's in teal, so it doesn't matter. So that's 3rt minus 2. So here it's a little bit simpler, and this is just a property. When we add a positive slope and a negative slope, it equals to 0 because the slopes cancel out. So just here I think you'll understand a little bit more. So this is basically what's going on with the unit step function and the ramp function. Went over how to describe a expression for a realistic unit step function, and an expression for a ramp function, which is the integration of the unit step function. I'll see you in the next one. Bye.